Next topic we're going to be talking about is line integrals. And in order to understand line integrals, we're going to actually use some motivation from physics, and we're going to use the concept of work. Okay, so what is work? That means if you're pulling, this guy is pulling an object on flat ground, and he's pulling it this way, then he's doing a certain amount of work. So if I ask someone to pull a box 1 meter, they might not be too upset. That's not too much work. It's a little bit of effort to get to move 1 meter. If I ask someone to pull a box 1,000 meters, they're going to be a lot more upset because I've asked them to do a lot more work. In intro physics, if you took it sometime in high school before you knew calculus, then you knew they usually use D. Work was force times displacement, or force, we're going to use X, force times the amount that we moved. So, like I said, 1,000 meters is 1,000 times more work than 1 meter. And then the other thing is the force matters. So if I pull it 1,000 meters and I pull it really hard the whole time, I'm going to be exhausted. Probably can't do that. I probably don't have that much energy in me, actually. And energy is a technical physics term as well. But if I'm going to go the 1,000 meters, I'm probably not going to exert myself that much. I'm going to use a low amount of force so that I don't do so much work. It might take a little bit longer, and that's okay. We don't measure over time, at least for work. I believe that's power. Okay, so this was your very first physics class, and we're measuring work as we have a constant force. You're pulling the same amount of force all 1,000 meters, so maybe not super realistic, and it's in the same direction as the displacement. And that's very important. So we're not wasting any energy here. Okay, and then maybe at some later date you learned about vectors, and you realized that this wasn't realistic. So let's say this guy's really tall, and this box is on the ground, and he doesn't want to crouch down, so he's pulling. The force vector is going a little bit slanted, but the box is still staying on the ground, so the displacement vector is still parallel to the ground. Okay, well then your equation suddenly became work was still a scalar, because we want to calculate basically how tired the person is at the end. So then it was a dot product, which, as we know, is the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Theta is the angle between them. So if you pull up really high, your cosine values are going to be really small. So your actual work done is pretty small, meaning there's a lot of energy wasted. Okay, so small amount of work of actual work done means lots of energy wasted, or lots of potential work. We'll just say energy. Lots of energy. I'm a little hesitant. I know a lot of these are technical terms in physics. Okay, so this situation was slightly more realistic. We still had a constant force, but now force was a vector, and it could have been in a different direction. It could still be in the same direction, but it could have been in the different direction from the displacement. Okay, and then as we got more realistic and learned a little bit more math, we realized that applying a constant force, especially over a long distance, is probably unlikely. So in Math 125, or your first integral calculus class, you learned that work was actually the integral from the beginning to some endpoint of some force function, which depended on x of dx. Okay, so notice we're back to one dimension. So we're back to the same constant. I should write this in gray to be consistent. Same constant direction as the displacement. But now we have a variable force. And we can think about what these functions mean. Like if we just take, for example, the function f of x equals x, this is a pretty unlikely force. That means you're not exerting any force at the beginning, and the amount of force increases linearly as you progress. So I don't know, maybe more realistic would have been f of x equals 1 over x, where x starts from, let's say x starts from 1 to 10. You're pulling from, then you start with a force of 1, and as you get, once you got up to 10, you're at a force of 1/10. So you get really, really tired. Something like that. Maybe the most realistic or the most productive would be like 10 minus x or something. Anyways, you can put whatever you want here. You can put trig functions, you can put roots, logs, whatever. We don't care. Okay, so you already know how to do that. Now in this class, so one thing that we want to do, we want to keep the force variable. I'm not switching to gray again. Okay, we need to keep the force variable because it's not quite realistic to do a constant force. And now we're still at first going to stay in the same direction as displacement, but it's going to be a varying direction. So looking over here, we're moving in the x direction. But like, what if you're in the plane and like, okay, this is a bird's eye view now, and like you have your object and you're pulling it, and like you don't just want to pull in the x direction, you want to pull in some crazy path and end up here. Then it doesn't make any sense to just calculate work done here. You've done a lot of work going all the way around in this loop. So we're going to do that. Okay, so now your work is going to be, we're going to call this curve C. So the notation is we're going to integrate over the curve C. And we're going to have your force function, f of x comma y comma z. So it's a variable force. It's dependent on where you are in the plane. And ds, remember s kind of stands for arc length from 126. So every small increment you go, we're multiplying by this arc length. That way, if it's really curved, it might contribute more or less, depending on, I think more. Yeah, really curved contributes more. Okay, and then all we need is this formula. ds by dt is actually the absolute value of the speed, right? Okay, so arc length or speed. Well, no, we'll call, this is the change in arc length, so delta arc length, and then we think of ds by dt as speed. That's really what that is. Okay, so then we can do this little sketchy thing that I always tell you never to try at home, but we can kind of multiply both sides by dt. So ds we're going to write as the magnitude of r prime of t dt, where r is the parametrization of this curve. So r of t is your movement vector. Okay, so then we get this formula. We're integrating from some beginning point to some ending point. So here's, like, we started at the point r of a, and we ended at the point r of b. So usually t is between a and b. And then you've plugged in r of t. R of t is going to be literally this vector, x of t, y of t, z of t. So we plug that into our force scalar. And then ds we replace with magnitude of r prime of t dt. Okay, great. Let's do an example of this in the next video.